Thanks, guys. I'm going to try to get the screens adjusted here, if I can find them. Woohoo! We're clicking gas. All right, my name is Tim Ojo. Just a quick poll. How many people have had some sort of experience with graph database? Either you've done some research on it, you've used one in test, or played around with one, or you've actually thrown one into production. I see some hands. Oh, really? Nice, awesome. I've actually met some of the guys at GraphStory, and I've worked with them a little bit. That's cool. All right, so I guess for the rest of us, we're total noobs, which is good because this is going to be a pretty introductory course. I'll try to dig deeper as I go along, but it just depends on how much we'll have time for. But real quick, just an outline of what we're going to be talking about. We're going to be talking about the history and landscape of today's databases and how that birthed graph databases. A teeny little bit of graph theory. I'm going to be modeling with doing some data modeling with graphs, and then a demo, and hopefully some questions and wrap up. So hold on to your seatbelts. But before I go into that, just a little bit about me. I'm a developer at AudiencePoint, which is a email analytics startup right here in downtown Chattanooga. Got some people over here who are interns over there. Also followed to a boxer Weimaraner mix. Super energetic, the most adorable 1-year-old ever, as judged by a jury of his peers. And I got my wife knocked up again, because that's what I do. I also blog at timojo.com, and if you go check it out, you will increase the readership to 2, which is great. So please do that. It's a mix of technical articles and also some soft science stuff. For example, like the latest blog I've got is how to be a kick-ass developer teammate, and checking in broken code isn't one of them. All right, one last thing is there will be no GIFs in this talk other than these, just because I am not a really great speaker. I'm just trying to do my best not to bore you. So enjoy these. This will be the last you'll see. Let's jump into it real quick. So every developer has sort of the idea of persistence in mind. You write some code. It does some processing. And it's got to store data somewhere. And for the past 35 years, the gold standard in that kind of persistence has been the relational database. The relational database stores data in tables which have rows and columns, and relations are implied by matching keys in 2 tables. So you could take 2 keys in a table and do a lookup for the matching relationship. We also normalize our databases. You can normalize it up to 6 normal forms for storage efficiency. I know 6, it's a lot. Yeah, if you go past 3, you're a crazy person. But you can go all the way up to 6 for storage efficiency, and we adhere to ACID rules. Relational databases adhere to ACID rules, and this has been great. This has been great for the longest time, for 35 years. And then the guys over at DARPA gave birth to this thing called the intertubes. And the intertubes gave birth to these companies called Google and Microsoft, not Microsoft, Google and not Microsoft. Google and, nothing against Microsoft, and Amazon, companies that had to deal with massive amounts of data. And they found some breaks, some chinks in the armor start to develop in relational databases. One is that they got really hard to scale. It became hard to scale them up to a certain point. The reason for that is relational databases scale vertically pretty well, but not horizontally. So you can't spread the data in a table across multiple nodes. You can only add more horsepower to the node that you've got. So we've got these machines, they've got 12 terabyte SSDs and 128 megs of RAM. Just to run a database, but you can't just pop up a new node if you needed to shard your data. The other thing with relational databases is because you have to do joins for relations. Once your data size gets to a particular point, joins become really slow. Because for a join, your SQL engine is taking the data from the first table that it needs to join and the second table that it needs to join. It creates an intermediate result set. And if you have multiple of those, you have multiple of these intermediate result sets. And if they get too big to fit into memory, it goes to, it has to do some disk operation. And once it starts to do some disk operation, you might as well just go get some coffee or something. So the scaling became an issue for relational databases. Not only that, but some data models don't map cleanly or easily to the relational data model. The simplest example I can think of is lists. So say you have a person, and this person has certain aliases or so. A person record, John with the email, whatever it is, and you want to have aliases to that person. Maybe Johnny, Johnny Boy, JB. Jack or so. One thing you could do is you could have alias 1, alias 2, alias 3, alias 4. Well, that's obviously nasty. You could also create a separate table just for aliases, but that's sort of overkill. All right. The relational model didn't map perfectly to a bunch of things, and then also relational databases require predefined schema. And you have to sort of get it right the first time, because to make any changes to it afterwards is painful. If you're adding stuff, it's fine, but if you're taking stuff off, it's painful. So we birthed the NoSQL movement, came out of that. NoSQL generally is the most popular type of NoSQL databases are key values or document stores. And generally those are really scalable horizontally, because you could just shard your data, right? You can just shard your data, spin up multiple nodes, and distribute your data over there. You could geolocate your data closer to where your customer is, and those kinds of things. Also, NoSQL brought flexible schemas, so you're not tied into the schema of a table or so. Your document could have it could be deeply nested. It could have lists. It could have, arrays in it. Different data types that you might not get in a relational database, and you could change that easily. So your schema could evolve as fast as your code can, because a lot of times we don't develop waterfall anymore. We develop agile. So our code continually evolves, but we could get constricted by our database because we can't change something because it's already been set in stone. So that was the NoSQL database was formed to sort of address some of the chinks in the SQL armor, and we've got key value stores, document stores, column stores, XML stores, and now we've got, drumroll please, graph databases. All right. Here's a definition of what a graph database is from the source of all truth, aka Wikipedia. In computing, a graph database is a database that uses graph structures for semantic queries with nodes, edges, and properties to represent and store data. A graph database is any storage system that provides index-free adjacency. This means that every element contains a direct pointer, so it's a JSON element, and no index lookups are necessary. A couple of things to consider from this definition. Definition is graph databases use nodes, edges, and properties to store data, and we'll see that a little bit when we take a brief look at graph theory and just graph databases in general. Another thing that I thought that stuck out to me is index-free adjacency. Right, there is no need for lookups when you're trying to do relations between two entities, right? Because instead there is a direct pointer from a particular entity to another entity. And also semantic queries. Now, what are semantic queries? Again, from Wikipedia, semantic queries enable the retrieval of both explicit and implicit derived information based on syntactic, semantic, and structural information contained in the data. They're designed to deliver precise results or to answer more fuzzy and wide open questions through pattern matching and digital reasoning. Now, that sounds like a whole bunch of computer science nerdy stuff, which is awesome. I don't understand it, but it's awesome, so let's go with it, right? Well, too much honesty there. Actually, what it is trying to say is you can infer some information just based off of the structure of the data by itself. And that's one of the things that graph databases can do, semantic querying, that you won't find in any other sort of NoSQL solution. So the reason why a lot of people haven't heard of graph databases is they just sort of came in 2011, 2012. They sort of came into the mainstream developers mindset or tool set, I should say. This graph is probably a little misleading because you might think that it's saying that graph databases are more popular than relational databases or any of these NoSQL databases. Actually, what it's saying is that the increase in the interest in graph databases far outpaces those of other databases. That's a 500% increase in interest over 2 years. Actually, the top 10 popular databases, I think it's Oracle is number 1, and so on and so forth. I believe there are 4 NoSQL databases in the top 10. You don't hit. It's not until you hit number 22 that you find the first graph database, which is Neo4j, which is the one I'm going to talk about today, or focus on today. But the adoption is growing and interest is growing. And there's actually a Forrester Research article that says that graph databases would hit 25% of enterprises by 2017. So here's your sort of chance to jump on the gravy train while it's still rolling. Who makes graph databases? Neo4j's got one. OrientDB is a multimodal database. Multimodal meaning it's both a graph database and a document store. So you've got documents just like you would have in MongoDB, and these documents can also have pointers or relationships to other documents or other entities. And you could sort of query it just like you would a document store like MongoDB using key value, using key document retrieval, or you could do that and then traverse the graph to other nodes or entities. So it's pretty cool. There's Titan and ArangoDB. Microsoft has jumped into the graph database game with Graph Engine. I believe it's still in beta. Apache Giraffe was sort of a collaboration between Facebook and the Apache Software Foundation. I'm not quite sure if it's in active development right now, though, because the last release was November 11, 2014. I haven't seen anything from it since, so at your own risk. But the graph database users we've got today, these are just the big names. We've got lots of other smaller companies that you won't recognize there, but eBay, Walmart uses it for their recommendation system. eBay uses it for a sort of like a buy it now type for their buy it now, to back their buy it now type feature. A bunch of other companies use it: Glassdoor, LinkedIn, Cisco. And all right, graph theory for dummies. One of the things that stumps people when they think of graph databases, they think you have to be super nerdy or super geeky to use it. I think you've got to be understand graph theory, understand Dijkstra's algorithm, or Bellman-Ford algorithm, or birth first search or death first search. You don't have to understand all of that. Simple. Well. Pretty simple, relatively simple. There's 4 things you need to know to work with a graph database. The technical definition of a graph is a set of vertices, and which we think of as nodes. That's the big circle things, super easy. And edges, which are relationships. Both nodes and edges can have properties. That's what a property graph is. So as you can see, this node right here with ID 1 has 2 properties, name and age, and the relationship also has properties. And the edges can be directed or undirected. The relationships can be directed or undirected. So Alice has a direct relationship to Bob, starting on the date 2001 10/3, if I can read that correctly. And Bob has another relationship that goes back, but the date is different. So the relationships can be directed or undirected. Typically, they're directed, but you could traverse a graph, even a directed relationship, both ways in most graph implementations. And then queries involve traversals and /or index lookup. So you can look up Bob and then traverse from Bob to other parts of the graph. And that's it. That's all you need to know about graph theory to work with graph database. Database is pretty simple. So if you ask the salesman, why should I even bother? Why should I look at graph databases? Why should I look into graph databases? The first thing they'll tell you is relationships in graphs are first-class citizens. And what does that mean? As opposed to a relational database model where an index lookup is required, where we try to match two values in two tables. We pick up a value in a table and we go look it up in the other table to sort of infer that relationship. With a graph, there is a direct pointer, a direct relationship between the two entities, and not only is there a direct pointer, but that direct pointer is also stored in the engine as part of the data model. So this makes scaling sort of multiple hops, highly relational data, super simple, super easy and efficient. Instead of when you've got a join, instead of having to sort of pick up and then look up on one table and then look up on another table, the traversals are effortless based off of hops. So that's one strong argument for graph databases. Graph databases are also schemaless, meaning you could have two nodes that are of type person. Person node 1 could have properties name and age. Person node 2 could have properties ID and email and something else. There are two, there's no sort of schema that enforces that these have to have the same properties. That these two person nodes have to have the same properties. So you're free to sort of evolve your graph, your model however you want to as needed on the fly. So let's say your person node started out having age, and then you thought, well, that's stupid because age is a snapshot in time. What I really want is date of birth, and then I can compute the age later. Right, you could take out age and throw in date of birth, or you could even, you could have a slow migration where some nodes have age and some nodes have date of birth, and there is no problem. You could easily query those without an issue. Nothing enforces a schema on you. OrientDB does have an option, is schema optional, so you can with OrientDB say I want a partial schema, or I want a full schema, but that's totally up to you. And again, I've talked about this a little bit. Graph databases handle highly relational data and complex queries with ease. They can model things that are harder to model in a relational database. We'll show you an example of that, data modeling with graphs right here in the next slide. All right, this image is stolen from OrientDB, so I give them the creative rights back. I give back to them. I did not write this, but if you look at the first example, right, relationships based on context. So you could have a person that has sort of three different relationships to a company. They could be a partner in a company with ownership of 1%. They could be an employee. They could be a customer of that company. So you could have sort of lots of different relationships based off of the context in which your data model is operating at the time. And if you try to represent that in a relational database, you'd spend all day. In a relational database, there's a concept, in working relational database, there's a concept called object relational impedance mismatch. And that means that whatever when you're actually working in code, you've got these objects that you create, and you have to translate them into tables, into rows and columns to be able to store them into your relational database. And sometimes that translation is not clean, and sometimes that translation takes takes a lot of brain power. But with a graph, that mismatch is not there. There is an object graph mismatch, but it's really small. It's really compared to an object relational mismatch. Hierarchical data, graphs can do that real easily. Just because it just uses pointers. If you try to do that in a relational database, you would either have to have a predefined number of self joins, or you would have to try to do recursion within your SQL statement. And good luck with that. Let me know how that goes. Sorry. Cool, awesome. I would. Yeah. Yeah. Yeah, exactly. Also, something that a lot of developers have to deal with, on a day-to-day basis, many-to-many relationships with graph databases make that super easy. And so here's an example. Here's Jira's data model. Jira's data model is actually a relational database. They actually use a relational database, but someone took their relational database and sort of mapped it into a graph for the purpose of exercise. And as you can see, it maps really cleanly in a graph. The central entity is clearly the issue, but the issue can be reported by a user, can be assigned to a user, can have a status, can have comments there can be comments on the issue. There's this sort of project management arm of it where you could say a project, a sprint is part of a project. A sprint contains an issue, so the project has that issue. It's clear that this model is really cleanly to a graph, and you can walk these relationships and understand these relationships a whole lot better than if you're trying to read the schema. If you're trying to read a database schema, but this is an example of something that's commonplace because a lot of people use bug management systems all the time. Something that's a little less commonplace is identity and access management systems. Now this is the stuff that's written by the graybeards, the old Linux guys with the big glasses, the ones that encrypt everything because the NSA is out to get them. Those guys, right? The wizards. Right, this is their domain, right? But with a graph database, it becomes more accessible. With a graph database, you can see that if you can decipher a path, or if Cypher could decipher a path between, user Alice and this artifact right here, then she has access to it. And if a path can't be deciphered between those two entities, then she doesn't have access to it. So it makes it real easy. It makes it real easy to do. Well, not exactly real easy, but at least much more accessible when you can do that. So let's talk about Cypher for a little bit. Cypher is Neo4j's graph query language, sort of like SQL, but not at all like SQL. There are a couple of ways. There are a number of ways to query a graph. There's Gremlin. There is, I believe, Blueprints. And then you can use the native APIs of whatever the graph is written in. Most graph databases are written in Java. And you can use sort of the native Java APIs to traverse it. My issue with a bunch of those methods is that they're imperative, which means that you have to say exactly how you want to walk the graph. You want to start with a particular node and traverse down this relationship, and hit this node and traverse down that relationship, and all that. Cypher is declarative, like SQL. And it's based off of pattern matching. So you say, I've got a pattern, and go find me paths that match that pattern, or go find me nodes that match that pattern. And what I also love about it is it's based off of ASCII art. Yeah, which I love. It's awesome. Yeah, so if you're drawing a circle, you'd have two parentheses, right? And that's sort of what that is. And you'd have, if you had an arrow or relationship, you'd have dot, dot, and greater than, and then another circle. And this is valid Cypher right here. If you punch that into Neo4j, it would actually go match for you all nodes that have any relationship to any node. So basically, it will return to you everything. The only thing that it won't return back to you is a node that has no relationships whatsoever, right? But this is valid Cypher, and you can sort of narrow down your query a little bit, right? So you want to say only match me person nodes that have relationships to donut nodes, like Tim loves donuts. And this is valid Cypher as well. This shows you that your relationships themselves could have labels. They can also have properties, as we see down there a little bit later. So if you had, a person node that has a love relationship to a donut, and a person node that has a hate relationship with a donut, this pattern will only match those that have a love relationship with a donut, and so on and so forth. So person with the name Tim, which is that node right there, has a relationship loves to a donut with the type maple bacon, because they are delicious. True fact. True fact. Is there anything other than true fact? Yes, false fact, I guess. Go ahead.
I was just curious, in the person loves donut, there's no P before the colon, and there's no D before the donut.
Gotcha.
What are the P and the D?
So the P and the D are sort of variables that you assign to identify that node. It could be anything. It could be lowercase person. It could be any sort of symbol. But it's a variable that you can then use later on in the query, which we will see, to sort of refer to that node. But thank you. Great question.
Can I ask you a question?
Yes, sir.
In the final example, basically he really loves donuts.
Yes.
His love goes to 11.
On a scale of 1 to 10, he goes to 11.
Is the scale like an attribute of the property for the relationship?
Yes, exactly. The scale is a property of the relationship. So a property can have relationships as well. A property, for example, the example that we saw in the past, where you had Bob and Alice, and Bob has known Alice since 2011 or something like that, right? That since 2011 is a property on the relationship, and you can have as many properties as you want on a relationship, and those are also searchable. Unfortunately, I found it hard way in Neo4j. They're not indexable, but they are searchable. So if you don't put anything you want to index on there, or it'd be really slow if you wanted to search off of that, but they are searchable, absolutely. Did I answer your question?
Yeah. Great,
thank you. All right, so let's say we have an order recommendation system. Alice, Bob, Mr. X, and Mrs. Y. Alice knows Bob. Alice knows Mr. X. They've bought certain things or whatever it is. All right, and I know I'm sort of throwing you in at the deep end, especially if you don't know Cypher. But I feel like it's pretty readable still. So what you want, right? Your recommendation query is if I've bought a product, find me other customers that have bought that same product and recommend to me the products that they've bought. So kind of like the Amazon model of, I see you've bought, bread. Other customers typically buy milk and eggs. Do you want to add this to your cart type deal? Here's the query. The query says, match customer with the ID of 101, right, who has a bought relationship to a product. Match other customers, peer, we have the variable peer to identify them, peer, that also have a bought relationship to that same product, and give me the products that they have a bought relationship to. It's fairly intuitive. Fairly. Right? We say we're not you, that's the initial customer, also has a bought relationship to that recommendation. So if other product, if I bought milk and eggs and other customers buy bread and milk, I don't want to be recommended milk as well because I already have it. I already have it in my cart, so I only want to be recommended bread. Then there's some returns, return the recommendation and the count as frequency, the frequency of the recommendation, and order by the frequency and only give me the top 5. So so give me the most common recommendations for that. Again, like I said, fairly intuitive. If you know Cypher, it's pretty easy to reason what this query is doing. If you wanted to do this in SQL, yeah. This is 6 joins. This will not scale at all. Frankly, if you can read it in 5 minutes and understand what it's doing or what it's saying, I might be tempted to name my kid that's coming up after you. Yeah, you would be a genius. It's not going. Oh, awesome, live demos. We got some time. I was hoping we'd have time for live demos. All right, so let's see. Cool. And I can barely read this. So let's see if I can jack up the font size. Is this readable? Oh yeah. Thanks, Phil. Cool. All right. So I've got in here in my Neo4j instance, and this is what the Neo4j sort of console looks like. There's this little tutorial that shows you how to start. Things like that. Over here, the console is the web console. There's also a command line console. But over here, it gives you a little bit of, and I don't know how to drive backwards. There we go. Gives you a little bit of information about what nodes and properties are in your database. Here, you can sort of save some queries in hand and save some queries. And here's just some help text and stuff. That's a quick look through the console. And in here, I went and grabbed database from grabbed information from the Department of Transportation, flight information from the Department of Transportation, and using some Python scripts with the help of Nicole White, threw some data into this graph. So. I can write a query that says, and I've saved this just for time. I've saved this just for time and said, give me states with the most airport. So I've got a match, my match, which matches my pattern. Give me all airport nodes that have a relationship, an in-state relationship to all state nodes. I want to return, and that's where the and this is where the little variable matters, right? I want to return the name as state, and I want to return the count. I'm going to order it by count, and just get the top 10 of that. So if I go ahead and run this, it tells me that Texas has the most states. Most airports, sorry, followed by California, Florida, yada, yada, yada.
Is the aggregation implicit in that query?
Say it again?
It's aggregating on state. Is that implicit within the count?
Yes. In your return clause, you can aggregate, and there's a bunch of aggregation functions that here's a little quirky thing about you. They have to be placed in the right place, but if they don't get placed in the right place, it'll complain anyhow, and it will aggregate for you based off of the state. So let's say we wanted to find cities in Chattanooga with airports. This is an even simpler query, really. It matches any city that has a in-state relationship to a state with the abbreviation of TN. So it goes and finds, and actually, one thing I could do is I can ask it, I can profile the query, right? And which tells me it scans all the state nodes, finds the state Tennessee, right? Then it expands out, it crawls the graph to all the cities and filters the city and returns my results. So my results are Bristol, Chattanooga, Memphis, Knoxville, Tennessee. These are the cities with airports. For time, I'm going to just sort of jump through a little bit. Find flights out of Chattanooga. Let's look at what this is doing. So it says match the airport Chattanooga, and give me all the flights that have the origin Chattanooga. There is also a graph view of this, and also limit just 10. There's also a graph view of this that shows you these flights. And if I wanted to, well, with Neo4j you can't edit the graph. The graph is just for visualization purposes. With RDBMS, you could do some sort of edits with the graph, and you could do some sort of manipulation with the graph. But Neo4j doesn't have that, even though I think Neo4j is sort of a nicer graph database. But if I wanted to know what the destination of these flights were, right, what I'd do is I'd say, so that flight has a destination, I want to make sure I spelled that right, to another airport. I'm going to call this A2 because I already used A. I didn't. It's hard typing backwards for me. A2. Let's give this a label. I'm just going to call this D. So I'm going to go ahead and return D. I think this is valid query and this should work. Yes, it does. Awesome. So we could see all these flights that started out at Chattanooga and ended up in Atlanta. Clearly, right? Most flights out of Chattanooga go to Atlanta. And there's a bunch of other queries that I could run, but because of time, well, here's a fun one. And this is actually a granddaddy one. So match a flight. Match all flights where that took place on this particular day. Go find their aircrafts. And now collect all those flights into a list and give me the count, the size of that list. That's as count. And we're going to return, what's A? The aircraft, the flights, and the count. We're going to just limit it to the top 5. So if I go ahead and run this, let's see if we make this bigger. We see, right, this aircraft that had, a bunch of flights. This aircraft that also had a bunch of flights. Right, if I look in, please render, please. Okay, I'm not sure what's down there. There we go. All right, if I look at the rows view, you can tell there's actually a flight an airplane that had 15 flights in one day, which is mind-boggling. Right? How do you do 15 flights in one day? If a flight takes 2 hours, right? You can do 30, right? Right? You got to do 30 hours. However, I did a little digger deeping. I did a little deep dive and found out that with a little bit more extensive query, and found out this flight, actually, they're all Hawaiian. They're all to Hawaiian islands, so it's really, really short hops between these islands. So that's why I could do 15 in one day, which is amazing. So I'm going to sort of stop the demo portion and see if anyone's got any questions.
Do you have an example of an insert or the equivalent of an insert?
Sure.
What it looks like?
Sure, absolutely. So if I wanted to do an insert, it's a create statement. So I say create, if I can type backwards. Create airport, I'm going to give it an abbreviation, CHA. There we go. And this is a valid sort of SQL query. It's a create. You're creating a node, and you could have multiple. Properties. It's not just one property. So you could say location. South, east. And coolness factor 11. You could also do, if you want to visualize it, you do a return A. Right, and so we just created this airport. Abbreviation char, location southeast, coolness factor 11. And these data types are because this is based on Java, these are any sort of JVM supported data types. And they are native data types, not object types. So you can't represent dates as a date object. You can only just do the year, month, unfortunately, at this time. Yes, sir.
So you got a potential collision there with another airport that's already defined by your abbreviation. Is there a way
Yes, I did.
to police that or to say, okay, you can only have a unique abbreviation?
Yes, you can. Actually, and that's great. If you type in schema, you can find out, you can see what indexes you've got. So I've got the tail number has a uniqueness constraint on it. There is an index on the abbreviation, but there's not a uniqueness constraint on it. That's why I can make another CHA. But yeah, you could have unique constraints on it or just index particular properties.
So it would be something similar if I wanted to just create a relationship between the two objects. I do a
Yes.
create node one, relationship one.
Absolutely. So you would do a, I don't know if I have time to type it right now, but yeah, you would do a create node one, relationship one, right? And then or actually you could do the entire create in one line. So let's go ahead and do that. Chat, which has an in-state relationship. Just going to call this R to another node, city. I hope there's not a uniqueness constraint on it because it might balk at me. Right, so this would create, this is a string type. just like in Java. Oh, I didn't return. My return statement didn't include any of those, so it didn't show you the graph of it. But yeah, it would have just shown you the graph that it just created.
But that creates an airport node with
Yes.
an in-state relationship to a city node.
Yes, correct. There is a merge statement that would do, and what a merge statement would do is it would create if not exist. So it will look for a path. If you say create airport with the relationship chat and these two exist already, it'll only create the relationship. If only one of them exists, it'll create the other two that don't exist and that kind of thing. It'll look for whatever path that you specify, that you try to match in your Cypher, and create what does not exist in the path. Yes, I think so. So let's get out of this. Anyhow, I don't know where my other slide went, but that's all I've got. If you wanted to learn more about Neo4j, there's getting started guides on their website. RDB also has getting started tutorials. It takes about an hour or so on Udemy. There's also free books available. You can contact me if you've got any more questions. I'm on LinkedIn. I've got email, so just walk up to me and talk to me later. And of course, I've got that blog thing out there. So thank you very much.